Welcome to the second day. The first talk this morning will be George Boxer giving his first lecture on p-adic automorphic forms. Just a reminder, after the talk, we'll have a group picture. We'll have a group picture after this. Are we ready to go? Put this on? Yeah. Like this, is it fine? Is it good or? Yeah. And this goes. I think this goes above your head. Like that. Okay. All right. So I should start or? Yeah. All right. So I should start or? Okay. Great. So thank you very much for the invitation to speak at this school. So I'm giving the first talk in a series of 3 talks on p-adic modular forms, where the other 2 are going to be given by Vincent Poloni and Louis Pan. And so I should say that in some sense, there's going to be very little continuity between my talk and the talks of Vincent and Louis. So if you don't like my point of view, then you should definitely still go to Vincent's talk, because it's going to start completely from scratch. And so my talk, it's going to be a little bit more old-fashioned. And what we decided is that we're basically just going to talk about the case of the modular curve, because it's already sort of complicated and interesting enough. So what I'm going to talk about today is basically the sort of integral theory of p-adic modular forms and of ordinary p-adic modular forms, which is what is called Hida theory. So let's begin with some notation. And please let me know if I'm not writing big enough or moving the board high enough. So I'm going to take P to be a prime. I'm going to take N to be an integer coprime to P, which is going to be some level structure. And I'm going to introduce a modular curve. So I'm going to let X over ZP be the modular curve of level gamma 1 N. And this is going to be the sort of proper one, so the one where we add cusps, although I'm really not going to talk much about cusps in this talk. So this is a moduli space of elliptic curves, which I'm usually going to denote by E, with a point of exact order n, or a section of exact order n, which I'm basically never going to mention for the rest of the talk. So it's not really going to play much role, but I just emphasize that this modular curve, it has no level at P. So it's sort of spherical level at P, and eventually we're also going to consider modular curves with some level at P. So X over ZB is a smooth proper curve. Okay, and so on this curve, we have the sort of modular sheaf, which is the sort of sheaf whose sections are modular forms. Yeah, okay, so maybe I should put like generalized. Yeah, so I'm going to repeatedly kind of ignore the cusps, as I said, and this is the first instance of it, but thank you. Are you happy? Okay. Okay, so this is the modular line bundle. And so I define it as follows. So we have a universal family of generalized elliptic curves, or semi-elliptic curves or whatever, and we consider the identity section, and omega is just going to be the sort of Colli algebra. So I'm going to use throughout this talk this notation omega sub E whenever I have some kind of group or p-divisible group or formal group, omega E for its Colli algebra. So this is the pullback along the identity section of the sheaf of relative differentials of the universal elliptic curve. Okay, and so the point of introducing this line bundle and calling it the modular line bundle is that so the sections for an integer k are exactly what are called weight weight k modular forms of level gamma 1n, except for the fact that somehow usually we define modular forms over the complex numbers, and here I'm working over ZP, so this is some kind of ZP lattice in the space of weight k modular forms of level gamma 1n. Okay? So what are p-adic modular forms? Well, so I'm going to write Gothic X, and throughout this talk, Gothic S will be the p-adic completion of schemes over ZP. So the p-adic completion, or the formal completion along the special fiber. And inside that, I have the ordinary locus, which is, so this is a Zariski open formal subscheme. And this is, in fact, a sort of affine and formally smooth over ZP. Okay? So, and the most basic definition of p-adic modular forms is that, so we have a restriction map which goes from sort of what we call classical modular forms, so the section of this line bundle on the whole modular curve, to its sections over the ordinary locus. And this is what we call p-adic modular forms of weight k. Okay, and so the point is this is kind of a huge space, unlike this, which is maybe a finite ZP module. And in fact, I mean, if you don't really like formal schemes, really all this is it's just the limit of the sections over the ordinary locus mod p to the n. And so if you think already about the case that m is equal to 1, so then the ordinary locus just over fp is an affine curve. So in some sense, we're taking modular forms of weight k, but where we allow arbitrary poles to supersingular points. And so that's an infinite dimensional FP vector space. And so you see that this space of p-adic modular forms is a big space. Okay. Can I raise the blackboard? Yeah, sorry. Okay, so now the thing which kind of makes this interesting is that we can consider p-adic modular forms of more general weights. And so the idea is that, so on XORed, we have a short exact sequence of p-divisible groups, which is somehow the connected étale sequence of the p-divisible group of the universal elliptic curve. So here, this is an étale p-divisible group. And then this is a sort of connected p-divisible group, and in fact, it's multiplicative. By which I mean, for example, that its dual is étale. Because in fact, maybe we have some kind of V pairing on E, and that's inducing an isomorphism between the quotient and the dual of the sub. And so what does this bias? Well, so I mean, so this modular line bundle, well, it can also be viewed as the Lie algebra of the entire p-divisible group. But since the p-divisible group has this sort of étale quotient, it's really the same as the Lie algebra of the sort of connected part. And now what you see is that, I mean, this tells you that this line bundle, it kind of has more structure than a line bundle really deserves to have, because this p-divisible group is kind of rigid since its dual is atal. So it's sort of, well, okay, let me actually just say more precisely what I mean by this. So let me introduce what I call the Igusa tower. So we'll consider some tower of finite atal covers of XORed. So I'll call this Ig_n, and then sort of at the limit of the tower, we have what I'll call just Ig. So what are these? So on Ig_n, we fix an isomorphism and on Ig, we fix an isomorphism between the whole multiplicative subgroup and mu p infinity. Yeah, so what I'm saying is that, yeah, so giving a point of this space is the same as giving a point of this space plus such a datum. Okay, thanks. So what property do these spaces have? So Ig_n that. Sorry, what is? Sorry, yeah, sorry. These are mu p infinity. So these are the, yeah. Okay, so this is finite atal. With Galois group z mod p to the n z cross. And the point is that this is the automorphism group of mu p to the n. And somehow the way to understand this is that you should just think about the automorphism group of the dual, which is an atal group scheme. And similarly, Ig to XORed is now profinite atal. With Galois group ZP cross, which is now the automorphism group of the multiplicative p-divisible group. Okay, so what that means is that over Ig, we have a trivialization of the modular sheaf omega e. So as I said before, it's the same as the Colli algebra of the multiplicative p-divisible group. But now via our chosen isomorphism with mu p infinity, this is the same as Colli algebra of mu p infinity. And now that's just trivial once you choose your sort of favorite basis for this space. So for example, you can send 1 to somehow dt over t or whatever you like. And so now we have trivialized omega e on this cover. And so we can do a bit better. So the point is this isomorphism, it's not ZP cross equivariant precisely because this differential here is not invariant under ZP cross. And so if we take that into account, so we have an isomorphism with what I'll slightly confusingly write O ig x. And here what I mean is, so we twist the ZP cross action by, so what x here means is somehow the character ZP cross to ZP cross, which sends sort of A to A, or X to X if you'd like. Okay? And so in particular, by descent, we can describe weight k p-adic modular forms as some kind of functions on the Igusa variety which transform in some way under the action of ZP cross. So in other words, we have that this space, which I called p-adic modular forms of weight k, is the same as the ZP cross invariance. Sorry. But now where we twist the ZP cross action by this character x to the k. Okay? So, sorry, maybe I should move this up a bit. So now we can use this to define p-adic modular forms of more general weight. So definition, a p-adic weight is a continuous homomorphism going from, so I'll write it as kappa, from ZP cross to R cross, where R is some ring which is complete with respect to the iodic topology for some ideal I, and we assume that P is in I. Okay, and so I'll give some more concrete examples in a moment, but now we can define so omega kappa on the base change of x ord to R by, well, we take OIG, we tensor with R twisted by this, with the ZP cross action twisted by this character kappa as before, and then we take invariance. Yeah, so here the character is the identity. And then here it's, so if you now take the sort of kth power of this, so this would then imply, for example, that omega e to the k is isomorphic to OIG x to the k, and somehow that's what I was using here. But now I'm saying, well, let's just take any character of ZP cross. Does it make sense? Sorry, okay, yeah. Yeah, sorry. So I mean the kth tensor power of, sorry, x, sorry, x to the power of k. So x to the power of k, it just means the character, yeah, sorry. Actually, now I realize I shouldn't have used this notation. I mean this group homomorphism. Yeah, and the bracket means a twist. Yeah. Sorry? 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 X is not a... no, yeah, okay, sorry. I understand, sorry. Maybe I really shouldn't have used this notation. So, I mean, yeah, so this is not, I'm not taking the sections, so this is just a sheaf, and I'm not taking its sections. What I'm doing is I'm defining a new ZP cross equivariant sheaf on IG, and I'm just taking the OIG, which is a ZP cross equivariant sheaf, but then I'm just twisting the action so that instead, when I act by some A and ZP cross, I also additionally multiply by A. And I think if you sort of meditate on what I said, like why does this not ZP cross equivariant and this is, then you'll understand. I'm just accounting for the action of ZP cross on dt over t. Okay. And so now we can take the sections of this, and that will be somehow the space of p-adic modular forms of weight k. And so somehow the idea here is that this definition is both sort of allowing us to take weights which are maybe just valued in ZP cross or valued in OCP cross, but it's also allowing us to take sort of families of weights. And and I'll give an example of that in a moment. In fact, there's just a universal weight, which I'll recall in a moment. But let me just state a quick lemma, which is again by descent. So the lemma is that this sheaf is actually a line bundle. Sorry, what am I reading? Omega kappa over X or R is a line bundle. And omega kappa, as well as the space M kappa, are compatible with base change in R. And so for M kappa, this is following from the fact that this is affine. Okay? So to give some quick example of p-adic weights, so first of all, I mean, the kind of weights which one would usually have in mind would be weights which are just characters to say ZP cross, or maybe to say OC cross, continuous characters. But we can also sort of consider families, and I'll just say that there's a universal weight and what ring does it live in? So let's introduce the Iwasawa algebra. This is a sort of completed group ring of ZP cross, which can just be defined as this limit. And so there is a weight, which I'm going to call kappa universal, which goes from ZP cross to lambda cross, and it's somehow defined by sending an element A here to the sort of, well, the element of each of these group rings defined by A mod P to the N for all N. That's all I mean by this notation. And so this is a continuous character, and it's universal in the sense that giving, so that there's a bijection between characters like this and continuous ring homomorphism. Okay, and so if you'd like, you can view this as a sort of lambda as sort of the moduli space of p-adic weights. And then for that reason, it, or maybe spoof of it, is sometimes called weight space. Okay? Yeah, so, right. So a classical weight is just an integer. And the integer that, so if you have an integer k, you take this character x to the k, and that's the corresponding p-adic weight. And I'm going to explain this a little bit more generally now. But does that answer your question? Yeah, so basically, like, you really don't lose anything if you think about either the case of OC, which you should view as like a field valued point, although it's not really a field, or this sort of universal one lambda, and maybe there are some quotients of them or something. Like in this definition, you could also, of course, take like OC mod P to the N. Okay. So now I want to explain a little bit better what is the relation between classical modular forms and p-adic modular forms. So I already explained that there are some maps, there are these restriction maps from classical modular forms with no level at P to p-adic modular forms, but actually the spaces of p-adic modular forms also see classical modular forms with deeper level at P. So I want to explain this. So I'm going to explain this in a slightly strange way, but I'll try to explain why I'm explaining it in this slightly strange way. So I'm going to let x1 p to the n m, so be the moduli space of E as before, plus an embedding of mu p to the n into its p to the n torsion. Okay, and I'm viewing this as a moduli space over ZP. Okay, so this exists. It's representable, but let me make some very quick remark. So this is not proper over ZP. Yeah, so the M stands for multiplicative, and it's because this level structure somehow involves this multiplicative group. Exactly. So this is not proper over ZP. And indeed, if you have a super singular, if E is like a super singular elliptic curve over FP bar, such a map can't exist. So this space, although it has a non-empty special fiber, it contains no super singular points, for example. So it certainly can't be proper. But on the other hand, if we take its generic fiber, and maybe we should additionally not just base change to QP, but add P to the n roots of unity so that we can choose an isomorphism sort of over this field between mu P to the n and Z mod P to the n. This is the usual modular curve of level, I guess, gamma 1. So there's still this level n structure floating around, which I'm kind of ignoring, times P to the n. Okay? And so we can take the global sections, and so this is a lattice in the space of weight k modular forms. Sorry? Yeah, so at the very beginning of my talk, now erased, I had also this tame level. I had this prime to P level structure, which I was just putting there basically to rigidify the modular curve. And we're sort of subsequently ignoring it. So if you'd like, I could just put it there. I mean, so really this is like EP, where P is a section of order n. So I'm basically just ignoring it throughout my talk because it's not doing anything. We only care about P in this talk. Okay. And in some sense, I mean, I want to claim that this is the sort of usual such lattice. So this agrees with the lattice defined by integrality of a Q expansion at infinity. So if you look in lots of papers on modular forms, people want to work with modular curve or modular forms with some level at P, but they want to work P integrally. So they want to define some integral structure on this space tensored with QP. And in some sense, there's lots of integral structures on this space, and it's not so clear that there's really a good one or a best one. And for some reason, which, well, I'll maybe give some motivation for it in a moment, lots of people like to use this one, okay? So anyways, it is a thing, but now I can explain, oh, sorry, I'm supposed to go to the other side. Now I can explain what does this have to do with p-adic modular forms? Well, I mean, the idea is that you might have imagined that the definition of the Igusa variety looks a lot like I'm adding some level structure at P. And indeed, there's a close connection with this definition. Yeah, sorry. Okay. So we have a lemma, which is that if I take the p-adic completion of this kind of partial integral model, x1 p to the n m, is exactly the nth layer of the Igusa tower. And I'm not going to carefully write a proof, but in some sense, the idea is just that if you consider a point of this over some base where p to the n is 0, then you have inside here this kind of canonical multiplicative subgroup. And so that must be the image of this map. And so this map is really just giving you a trivialization of EP to the n m as in the definition of ig n. Okay? And so we also get some restriction map. Okay, and now we have an action of z mod p to the n z cross on well, both of these spaces. So the action is just given now by, again, multiplying on u p to the n. So I mean, I just remind you, this is exactly the automorphism group of mu p to the n. And so this is what people classically in the theory of modular forms call the action of the diamond operators. And so if we fix a character, yeah, so the m is just a notation. It stands for multiplicative, and the role it's playing in this definition is that I'm the way that I'm imposing this level structure, I'm asking for this multiplicative subgroup of EP to the n. And as I explained, I mean, of course, that's not giving you a proper integral model. So it's not a good definition of a gamma 1 p to the n level structure, but it does do the job for exactly what I'm trying to say here. What? Well, not well, by locally, it is on the part of the modular curve that I'm interested in, if that's what you mean by locally. Yeah. Yeah, exactly. Okay, so this is what in the theory of modular forms one calls a Nabin type. And what one does is one likes to consider somehow the. So I'm just going to introduce some notation for this. I'm going to call it M K gamma 1 t to the n. Maybe I should include the n, the capital N, but I'm not going to. Chi. This is just going to be the sections. Sorry. What am I writing? And then, so I still have this action of z mod p to the n z cross, and I'm going to take the chi inverse isotypic part of that. Yeah, I'm sorry. So is this illegible? Maybe I just write it again. And then I take the chi inverse isotypic space for the action of the diamond operators. And so just taking the isotypic parts of this restriction map here, we get a map to the space of p-adic modular forms. So I take the same isotypic space here, and that's the space of p-adic modular forms, as I defined before, of weight x to the k chi, where what is this character x to the k chi? Is the character which sends a to the k times chi of a. Okay, and this is an example of what we call a locally algebraic weight. Yeah, so I just mean the subspace, the invariance. So exactly as I defined before, I twist by chi and take the invariance. Yeah, so I agree that in general, this would not be exact. Yeah. Yeah, so this is this partial integral model, which I've just defined over there. And I'm just taking the sheaf, the same sheaf, if you like, the one pulled back from X. So the sheaf of weight K modular form. So yeah. So this is just it's just a subspace. So really all I'm doing here is I'm taking the subspace on both sides of this map, which are isotypic for the action of z mod p to the n z cross, and probably saying that in a very confusing way. Okay, but so what is the upshot of all of this? What we've seen is that this space of p-adic modular forms we've introduced, we have sort of these restriction maps, not just from modular forms of sort of no level at p, but modular forms with really level gamma 1 p to the n, and somehow the weight of the p-adic modular form, it sees both the sort of integer, the algebraic part of the weight of the classical modular form, as well as its Nabin typus, and the p-adic weight is somehow combining the two. Okay, so that's basically what I was trying to explain. So now I'm going to sort of get to theta theory. What kind of cohomology? Well, it sort of is what it is, and these are affine formal schemes. So you shouldn't be so scared of taking global sections. I mean, a sheaf is just a module over the global sections of the structure sheaf, and you're studying modules over some kind of huge ring, and that's what it is. Yeah. Yeah. Okay. So the basic problems in the theory of p-adic modular forms, or at least from some point of view. So first of all, there's a question of classicality, which is to sort of understand the image of exactly this restriction map So try to characterize, so you have this nice finite dimensional space of p-adic modular forms, or of classical modular forms we care about. It sits inside the huge space of p-adic modular forms, and you want to try to understand which p-adic modular forms are actually coming from classical modular forms. And maybe the other question is interpolation. And so this is sort of try to understand sort of families of Hecke eigenforms as the weight kappa varies. So that's a little bit vague, but so what Hita theory is about we have good answers to these questions for ordinary modular forms. So now I need to explain what does ordinary mean. So there's a Hecke operator UP, which is acting both on the spaces of p-adic modular forms and on the spaces of classical modular forms. And I'm going to recall in gory detail what this Hecke operator is in a bit. So right now I'm not going to explain it. And what Hita considers the UP ordinary subspace. And so what this means, so if I have M, let's just say for now a finite ZP module, and I have an action of an endomorphism which you can imagine is this some space of modular forms and some Hecke operator, then we get a decomposition, canonical decomposition, into a T ordinary part and a T non-ordinary part, and so it's T stable And the way it's characterized, or one way to characterize it, is that here T is an isomorphism, and here T is topologically nilpotent. Yeah, so this is just an abstract definition, right? M is a finite ZP module, T is an endomorphism. So right now it's just any endomorphism of a finite ZP module. And I'm telling you what, I'm just giving a definition. So I'm not going to prove this, but for example, one way to define, one way to describe this definition following Hida is that you take MT ord to be defined by some Hida idempotent, where T is defined as the limit of T to the n factorial as n goes to infinity. And so you have to sort of think about why this makes sense, why this converges, and then why does it do the job. But you can also give a sort of direct algebraic proof. Oh yeah, I'm sorry. Yeah, I know from being in the audience that you really can't see the low board. So yeah, I should remember to do that. Thank you for the reminder. Sorry? Ah, sorry. Yeah, you're totally right. Thank you. Oof. Yes. Yeah. So actually, maybe yeah. So I'm going to, in fact, yeah. So let me just first of all make a note that if you have a Hecke eigenform, so if F is in this space of modular forms, so there's this. So now we have this Hecke operator UP, where I'm going to tell you what it is in a moment. But if F is actually an eigenform, then F is in the ordinary space. If and only if the valuation of alpha is 0. So and sometimes this is the way that an ordinary p-adic modular form is defined. If you just assume that your modular form is already an eigenform for this Hecke operator UP, then being ordinary just means that the eigenvalue is a unit. Okay? And yeah, so maybe I should also sort of reiterate Peter's point that there's this very strange thing that we're defining p-adic modular forms as living on the ordinary locus, and then we're considering ordinary modular forms, which are ordinary in this sense. And a priori, those two usages of the word ordinary have nothing to do with each other. Okay. Yeah. Yeah, except that, yeah, so the slight issue is you don't really have an eigenspace decomposition integrally, right? But so this is in some sense what you get towards an eigenspace decomposition. So if you like, you can think of this as basically saying that like integrally, you have a decomposition into the generalized eigenspaces with unit eigenvalues plus the generalized eigenspaces with non-unit eigenvalues. But then maybe you can't refine that further, or at least for the non-ordinary part, you can't refine that further. No, yeah, so that's the other thing, is that I'm about to talk about the ordinary part of the space of p-adic modular forms, and then that also needs to be explained, and it will be explained a lot later. So let me go ahead and tell you what did Hida actually prove. So here's a theorem of Hida, which is from the 80s. And so it addresses exactly both of the questions I asked over there. So first of all, there's Hida's classicality theorem, which says that if you take an integer, a weight, an algebraic weight, which is greater than or equal to 2, So we had this restriction map from classical modular forms. And we restrict to the UP ordinary ones. And we also have the p-adic modular forms. And indeed, I'm going to now take the p-ordinary part without really explaining why it makes sense, because now this space is not a finite ZP module. So my definition over there doesn't quite make sense. You can in fact show that Hita's definition still makes sense, but you really have to justify that, and that will be part of the proof of this theorem, justifying why does this make sense. Okay? And the claim is that this restriction map is now an isomorphism. So this is what is called Hita's classicality theorem, or sometimes Hita's control theorem. And the second part is basically saying that there is a sort of universal family of ordinary p-adic modular forms. So in other words, it says that there exists a projective lambda module. And what you should think is it's basically gotten, well, I'll put it in quotes because you have to justify why it makes sense. It's basically gotten by taking the sort of module of p-adic modular forms with the universal weight and taking the ordinary part. Yes. I guess it will follow from the thing I'm about to write, but yeah. Thank you. There's a finite projective lambda module, which I'm going to call, M-ord, and it satisfies the following interpolation property. So if you take M-ord and you specialize somehow via the map from the Iwasawa algebra to ZP zeta p to the n, which is exactly corresponding to this character x to the k chi, you get, well, either of these two spaces. Okay, and so something that I'm not really going to emphasize, because we're not actually going to do any sort of number theory here. Sorry? Well, if I wrote the space of p-adic modular forms. So let me make Peter happy and write what he wants to write. Is it? Right, this is classical modular forms. Yeah, sorry. So let me actually just write the thing that Peter said, because it's probably a better way to put it. So this interpolates the space of p-adic modular forms of this weight. And indeed, now I could really just put any OCP valued kappa here, which is probably what I should have done. But then, yeah, and then if you further assume that k is bigger than or equal to 2, then you have the classicality theorem, and you see that it's equal to this, which is the thing that I wrote before. So in some sense, this module, it interpolates ordinary p-adic modular forms of all p-adic weights. And then in a locally algebraic weight, where the algebraic part is bigger than or equal to 2, those are actually the same as the classical ordinary modular forms in that weight. And so something that I'm not really going to emphasize, but all of these spaces carry actions of all the other Hecke operators, like the TLs, and there's TLs here, and everything is equivariant for all the Hecke action. And that's usually what makes this interesting. But yeah.
So I thought, so to my understanding, like the network is usually introduced to decompose classifiers. And then is this supposed to be like an analog of the statement, but for p-adic modular forms? But if I don't impose any condition on the neighboring types, then there are options of this module.
Yeah, essentially. I mean, right. So the point is, yeah, so it's exactly to deal with the fact that in this thing I wrote over there, like if I just restricted from the space of modular forms at level gamma 1 p to the n, I'll get a section of, sorry, it's written right here. I'll get a section on ig n. But this wasn't really one of my spaces of p-adic modular forms of some weight, because I defined them as sections of sheaves at the bottom of the tower. And so if I want to fix an eigenspace for the action of ZP cross here, I should also fix an eigenspace for the action of ZP cross there. And that's really the only reason I did it. But yeah, I have to admit, maybe this is something that's a bit confusing, and I sort of felt like I should have explained it, but probably I didn't do a good job. Okay.
Think about spatial-kinetic model for like not put couple universe at the.
Do we not put? We can, yeah.
So then, like, can you just define this law, this M port as literally that M a universe?
Yeah. So the point is you have to explain why it makes sense. But other than that, that is the definition. But I mean, in some sense, we already have the same issue on the line above. So, okay. So now what am I going to do for the rest of this talk? So my ambition is to try to explain somehow some idea in the proof of the classicality theorem. And so goal, I'm going to explain a robust proof of the classicality theorem at level gamma naught p. So I'm going to do it in a very special case just to make my life simple, but I want to explain an argument which is sort of not only working at sort of for the modular curve at level gamma 1 p to the n, but is essentially also working for lots of other Shimura varieties. So that's what I mean by robust. And so the rule here is that I'm not going to use anything which is particularly special to the modular curve, except just to help me draw some pictures. Okay? So in order to do that, so we're gonna work at this level gamma naught p. So I'm going to now try to be as concrete as possible and introduce some objects and draw some pictures. So let x naught of p over zp be now so now I'm going to take a proper integral model, and this is going to be the Dulin-Rappaport integral model. And what that means is it's the moduli space of elliptic curves along with a subgroup of order p. Okay, and since I didn't ask anything about this finite flat subgroup, like I didn't ask for it to be a multiplicative group or something, this will give us a proper integral model. Okay? And so we understand this model pretty well, but in some sense, I'm not going to use that understanding of this model. But let me describe some, so I'm going to take, as before, it's p-adic completion. I'm going to take the ordinary locus. And so now this has sort of two components, which I'm going to call xm and xet. And what are these? So this is the locus. So once we've forced our elliptic curve to be ordinary, then any finite flat subgroup has to either be a multiplicative group or an étale group. And these are exactly the locus where H is multiplicative. And this is the locus where H is étale. Okay? And sorry, maybe I should just do it over here. So in fact, we understand these spaces very well. So in fact, xm and xet are both isomorphic to the ordinary locus at spherical level. And I'll just tell you what are the isomorphisms so you understand what I mean. So what is an isomorphism from xord to xm? Well, I send an elliptic curve to an elliptic curve along with this sort of canonical multiplicative subgroup of order p. And how do I define an isomorphism with the étale locus? Well, I shouldn't use this elliptic curve, but what I can do is I can take the quotient by this multiplicative subgroup. And as my subgroup, I can take this group, which is now an étal group, right? If the P torsion is an extension of this multiplicative group by this quotient, which is an étal group. Okay, and you can, yeah. Okay, and I invite you to write down the inverses of these two maps. Sorry? Oh, raise the board. Oh, every time. Okay, and so in our kind of world where these are the kind of parts of x naught of p which we kind of understand, even though maybe we really understand the whole thing. So okay, so now I finally have to explain what is UP. Okay, and so we're going to start by doing this in characteristic 0, where we kind of feel that we understand what is UP. So, I mean, traditionally, like in textbooks on modular forms, UP is described by a formula like this one. So if we have a modular form and we want to apply UP to it, and we sort of evaluate that on an elliptic curve with a subgroup and get a differential or a K form on this elliptic curve, what it is that we sort of average over all subgroups of order P, which are not H. So we average over the P other subgroups of EP. So we're in characteristic 0, so they're just P plus 1 subgroups of EP. They're all étal. And we take the pullback of the corresponding differential on this other point of x naught of P that we write down using this subgroup L. And so here, this pi is just the isogeny from E to E mod L. Okay, and then there's one slight problem. We also divide by P. And this division by P is very important. If you didn't divide by P, you would get PUP. And you don't want to get PUP. Okay? But more on that in a bit. So let's try to write this more geometrically. So more geometrically, UP arises from a correspondence so I'm going to call it CQP for correspondence. So again, we're still only discussing the generic fiber here. So pi is the isogeny from E to E mod L. Okay, so let me just tell you what is the moduli interpretation of this whole diagram. So here, this is the moduli space. So the correspondence is the moduli of an elliptic curve and two subgroups. And I can just write down for you what are the two sort of degeneracy maps. So P1, and they're not the same. So P1 sends this to, you just forget L. And so I'm basically writing down the sort of things which occur in the formula I wrote above. And P2 is the thing that I wrote on the right. So it goes to E mod L and EP mod L. Okay, and so the idea here is that when you have this correspondence, you're supposed to think about the action on cohomology. So the correspondence is kind of viewed as a generalized function, which is sort of like pulling back by P1 and taking the image under P2. And the action on cohomology should somehow be viewed as the pullback under P2 on cohomology and then the trace under P1. And so we have a correspondence, and in order to define an action on cohomology, we need a bit more. We need something which is called a cohomological correspondence. Sorry? Oh my God, terrible. Yeah, thank you so much. Yeah. Yeah, I think I said forget L and then wrote the wrong thing. So to define an action on cohomology, we also need a cohomological correspondence. Which is a map. And for a reason I'm going to explain in a second, I'm going to call this map UP naive, which goes from this is a map on CQP. Okay, and so, well, yeah. So what should I say about this? So first of all, I'll explain what it is. And so this is built from. So first of all, we have this sort of analog of taking the pullback by pi in that formula up there. And that's going to be the pullback map, P2 upper star omega, P1 upper star omega. And so in terms of the moduli interpretation, P2 upper star omega is omega E mod L, and P1 upper star omega is omega E. And sure enough, we have a map like this, which is induced by the isogeny, now the sort of universal isogeny over C, E to E mod L. And the other thing we have to do is we have to do the analog of summing over the different points, which geometrically is like taking a trace, except I'm not going to try for the moment to divide it by P, although I certainly could in characteristic 0 without any problem. So the other piece is the trace map, which goes from P1 lower star of OC, or OCQP, to of x naught of PQP. And by adjunction, this is the same as giving a map, which is sometimes called the fundamental class, from OCQP to P1 upper shriek. Okay, and so what is this UP naive? Well, I'm going to take the kth power of this map, and I'm going to tensor it with this map, and I'm going to get such a map. And I should say, so how do we actually then define an action on cohomology? Well, it's like this. So, I mean, the point of a cohomological correspondence is that it's exactly the thing that you need to define an action on the cohomology of a sheaf. And what is the actual action? Well, it goes from, so we start in the cohomology of the space that we start in. We pull back by P2. Sorry, goes to C. And now we're in the pullback of the modular sheaf by P2. Now we apply our cohomological correspondence. So the space stays the same, but we land in the target of this map. And now there's a trace map under P1 because P1 is proper, or in fact, it's finite flat in this case, back to where we started. And the composition is what I'm calling UP naive. Okay, and so the claim is that if you really untangle this, the thing that you get. Yes, so yes, I have UP naive twice. So one is the map of sheaves. One is the map of sheaves, and I'm using it to define the endomorphism of cohomology. But I'm calling them both UP naive. And you're not going to be happy about that. Sorry. Okay, so what I claim is that if you untangle this definition, this more geometric definition, but just on the sort of H naught, you get exactly the thing that I described by this more classical formula up at the top, except multiplied by P, because I never tried to incorporate this division by P. Okay? Okay, now all the trouble in life comes from the fact that we now want to do something integral. Okay, so I'm going to define C, so no longer CQP, to be the normalization of CQP mapping down, well, let me write it like this, to two copies of X naught of P with the two projection maps. So by doing this, I produce some integral model C, which maps finitely to this product. And so in particular, the two projection maps extend, and it's normal. But a priori, I have no understanding of this space C. So I will say, though, that we still get, so C still carries an elliptic curve along with these two subgroups, H and L, which are now some finite flat subgroups of order P. But it is no longer the case that H intersect L is equal to 1. In some sense, this is a sort of, so on the generic fiber, these were all étale groups. And so this is a sort of locally constant condition. But once we work integrally with finite flat subgroups, this is sort of only an open condition. So there's some open where it's true, but it's not going to be true everywhere. And the way that you can immediately see that is if you take a supersingular elliptic curve, there exists a unique finite flat subgroup of order P inside of it. And so at every supersingular point of C, these two subgroups actually just have to be the same, at least at a field valued point. Okay? But anyways, it's a space. And so I'm going to make the remark that actually, okay, we do actually understand this space. So secretly, C is nothing but the Katz-Mazur model of X naught of P squared, but we don't want to use that because that's not robust. Okay? It is no longer the case. Yeah, it's not, I'm saying it's not true that H intersect L is the trivial group. So in general, they will intersect non-trivially. Yeah, so the integral model of Katz and Mazur, but we're pretending we're not going to try to use that. So yeah, so just to make some general remark, I mean, the point is, so this Hecke correspondence, it's so in general, we don't understand integral models of Schmor varieties with deep level at P. There's a sort of very well developed theory of Schmor varieties at parahorik level and pro P parahorik level, but this Hecke correspondence, it's sort of like x naught P squared, which is beyond parahorik level. So it exists in this world where, at least for more general Schmor varieties, we don't have any good understanding of integral models, except that in this particular case, we have the Katz-Mazur theory using Drinfeld level structure, but this is something that's not considered robust enough to use. So we don't want to use it. All right. So now, of course, the question is, do we get a suitably normalized, so maybe by dividing by P or something, homological correspondence but now on C, so extending the one that I wrote down on its generic fiber. And so we view this as a kind of hard question, at least in sort of general. And the reason is we don't really understand P1 upper shriek omega k if we don't understand the singularities of this map P1. So on the generic fiber, this map was finite flat or even finite étale away from the boundary, and so it's sort of no problem. Integrally, I mean, it is in fact finite, but maybe a priori it isn't. And it is in fact also flat, but maybe a priori it isn't. So the only reason that I know that this map is actually finite flat is because of this Katz-Mazur theory, which I don't want to use. Okay? So what we're going to do is something, so we're not going to answer this question. We're going to do something which is a bit softer, but is still perfect for doing Hita theory. Yeah, maybe I should write down what is the isomorphism. So yeah, so the point is that, I mean, for a point of C, you have two isogenies, E mod L and E mod H. So now if you take the dual of this isogeny and compose it with this isogeny, you get an isogeny like this. And this is the gamma naught P squared level structure. And so the point is, you need to say that like this isogeny is a cyclic isogeny. And that's the same as the condition that H and L are different subgroups. Does it make sense? Okay, I'm not doing well on time, but so the strategy. So I'm going to define, so let C good inside C be the open where, well, the thing I said doesn't always happen, does happen. So be the open where L intersect H is trivial. So this is an open condition. And so I can consider this C good. And so the claim is that although we maybe pretend we don't really understand C, we are going to understand C good. Okay? So what we're going to do is, so this sort of step one is extend or UP to C good. And step two is sort of use the dynamics of UP to extend to all of C, but while modifying the integral structure. And I explain in a moment what do I mean by this. Okay, but let's do step 1 first. So I claim that we understand this C good pretty well. So indeed, let's take its p-adic completion. So Gothic C good is the p-adic completion of C good. And so I claim that this is again the disjoint union of something I'm going to call Cm and something I call C-et. And now this is contained inside the ordinary locus, but this containment is strict. So the point is that C good, its special fiber, is contained in the ordinary locus exactly by what I said over there, that in the, there can't be any supersingular points of C good because there's only this one subgroup of order P. So what is this? This is the locus where H is multiplicative, L is étal, and this is the locus where H is étal and L is multiplicative. And the point here is that there's more ordinary points are both étal. Okay? And so, in fact, both of these spaces, Cm and Cet, are again isomorphic to the ordinary locus at spherical level. And I'll even write down one of the isomorphisms for you. So we can send an ordinary elliptic curve. And now I'll take the elliptic curve, which is we quotient out by its canonical p-torsion subgroup. And what are the two subgroups? Well, we want a multiplicative subgroup, so we should take the p-squared torsion multiplicative subgroup mod the p-torsion multiplicative subgroup. And we want an étal subgroup, so we can take the p-torsion of the original elliptic curve E like this. Okay, and so I invite you to just figure out quite easily what is the inverse. So okay, that's not good. So now we have correspondences like this. So you check that under the two projection maps, Cm goes to Xm, and similarly, Cet goes to Xet. And moreover, we completely understand these maps because we can just write all of them down in terms of these isomorphisms with the ordinary locus, which I've written down over there. And so what you check is that this is an isomorphism, and this is also an isomorphism, so the P1 over here, and this is a lift of Frobenius, and this is a lift of Frobenius. And the point, where is this lift of Frobenius coming from? Well, it's exactly coming from the map x-ord to x-ord, which sends an elliptic curve to the quotient by the canonical subgroup. And so this map, I mean, mod P, this is the kernel of Frobenius. So this is a lift of Frobenius to this formal scheme. Okay? So we kind of completely understand the correspondence there. And so now we can do I have the level structure? Well, I mean, yeah, so these are exactly these open subschemes of C that I've described. So they have some kind of level structure. You have these subgroups H and L. No, but that was my, sorry, but that was my notation. Yeah, I mean, so X of M is the, X of M and X of L are the two components of the ordinary locus at level X, at level gamma naught P. Does it? No, I don't think so, but maybe I'm confused. Okay. So now we normalize, and so maybe I'm not going to explain this because I have literally no time. But what we find is that on CM, 1 on P, UP naive exists. So this map of sheaves exists, and it's non-zero mod P. And on C-et, 1 over P to the K, UP naive exists and is non-zero mod P. And so the way to understand this is you just think about the normalization of all the ingredients. So for example, on CM, we pull back by an étal isogeny, which is quotienting out by L. So that map is an isomorphism. We don't get any divisibility by powers of P from that, but then we're taking this sort of trace under Frobenius, and that's explaining where this 1 on P is coming from. Whereas on C-et, the map we're taking a trace for is an isomorphism. So the trace is not doing anything, but we're pulling back by a multiplicative isogeny, and that's where this P to the K is coming from. Okay, so I didn't explain that very well, but now we can just put the two together on C good. So it implies that so what I'm going to call UP, which is P to the minus the minimum of 1 in K, which is just taking the sort of worst of the two normalizations, extends to C good. Okay. Oof. Okay. So now I have very little time, and yeah. Where is my eraser? K is the weight. I mean, so this UP, it's a map. Sorry? Oh, sorry, raise it. Okay, so I'm okay, so I have basically no time, so I just want to say some sort of conclusion. So I'm going to introduce a Cartier divisor, which I'm going to call DM. And this is the Cartier divisor, which is somehow defined by the map of line bundles. So this is induced by the pullback by the sort of dual of the isogeny from E mod H to E. Okay. And so what I'm going to call the sort of dynamical result is that if we consider this Cartier divisor on x naught of p, and we consider the two pullback maps to C, so this is now a a priori not effective Cartier divisor on C, the integral model for the correspondence. And the proposition says that this is an effective Cartier divisor whose support is a complement sorry, what am I writing? Of this opened, which I called C good. So it's this Cartier divisor is supported on the complement of the good locus. So I don't have time at all to explain the proof of this proposition, but let me just explain how we're going to use this.
What is the
Yeah, so a sheaf, a line bundle with a section, which is not a zero divisor. But it couldn't be a zero divisor unless it's zero. Okay, so just to conclude, so as a corollary, for all n sufficiently large, there exists an extension, which I'm going to call UP again, from P2 upper star omega k, but now I'm going to twist so I'm going to now, instead of considering just the sheaf omega k, I'm going to consider a modification of it where I twist by a big power of this Cartier divisor, which is entirely supported on the special fiber. So it's not changing the, for example, the generic fiber of this sheaf. So of sort of UP to the whole correspondence. And better, and this is what classicality will follow from, if k is bigger than or equal to 2, and again, n is sufficiently large, we even get a diagram so what I'm going to do is I'm going to consider somehow the inductive system of these sheaves where I twist by bigger and bigger powers of this Cartier divisor. And I have these maps UP. And the thing which is even better is that we actually get a factorization like this. And so, yeah, so let me just conclude then. And so as a corollary, we get Hita's classicality theorem. So maybe Hita plus epsilon. For k bigger than or equal to 2 and n sufficiently large, the restriction map from the cohomology of x naught of p of the modular sheaf twisted by this divisor to the cohomology of the ordinary part. So the cohomology of the multiplicative ordinary locus becomes an isomorphism when we take the ordinary parts. And okay, I should really just stop here, but I mean, essentially, this is just a formal consequence of this, because what you should view this as saying is that somehow the UP operator is reducing the order of the poles along DM. But okay, I didn't explain it very well, so I stopped. Thank you.
Okay, are there more questions for George?
Yeah.
But is it essential that we have like deep level and then not some speed?
Yeah, no, so I just wanted to explain it that way because I was going to draw some pictures, which I didn't draw, but somehow, I mean, this same argument, I mean, you could have just started with x1 p to the n and defined this c integrally in the same way. And you have, I mean, and somehow the exact same argument works.
What about this multiplication with x et al and x1?
Yeah, so you still have so what you're going to do is that in general, you're always going to have these kind of two open subschemes, which will be labeled by m and et. And they're always going to be isomorphic, maybe not to the ordinary locus at spherical level, but to some layer of the Igusa variety, which is just exactly parallel. I mean, I didn't try to explain this because, as you see, it would have been even worse on the time. But yeah.
And this
Yeah, it seems pretty robust. Yeah, but at least I mean we've written, we have some drafts in the Ziegel case and Hilbert. Anyways, yeah, it seems very robust. Yeah. Yeah. So everything is integral here. Yeah, and I mean really, like if you took like h naught, yeah, and so the thing, yeah, the one thing is that this is a little bit different than this thing that I wrote before, where I took this partial integral model. But in fact, if you just take the h naught of this and you take n sufficiently large, it's actually the same space, because when you allow sort of arbitrary poles along this divisor, the complement, yeah, maybe I really should say is that the complement of this divisor dm is exactly this partial integral model that we were considering before to define lattices and spaces of modular forms with level at p. So, yeah. And maybe, right, so I didn't really talk at all about higher Hita theory, but one reason that you might be a bit more happy about this is that, well, there's, if you'd like to study higher cohomology, it's not very reasonable to work with the higher cohomology of partial integral models to define integral structures on higher cohomology. You should really work with integral, like proper integral models. But that's, yeah. Oh yeah, I think it is actually written there. It's just blended together with the n bigger than 0. Yeah. I'm not going to say that's your fault. The Eichler-Schmor relation. Well, I'm going to say not really, but maybe like this, some kind of understanding of like the ordinary locus of these modular curves probably is, but yeah. So we never considered the spherical Heck operator TP in this whole story. And the Eichler-Schmor relation, at least as I understand it, is about TP. Yeah, so this is for this Heck operator UP rather than TP. So UP is the one which exists when you have some level at P.